Hello friends, welcome back to the lecture series on linear differential equations. In previous lecture we have discussed variable coefficient form of linear differential equations. If your variable coefficient is x, then it is known as Cauchy's or Euler's differential equation. Now we move to the next type for variable coefficient form. An equation of the form an ax plus b raised to n. It is coefficient of nth order derivative of y with respect to x, where an is constant, plus an minus 1 into ax plus b raised to n minus 1. It is coefficient of n minus 1th derivative of y with respect to x, and so on up to a1 into ax plus b into dy by dx plus a0 into ax plus b raised to 0 into 0th order derivative of y, it is by itself, it is equal to f of x. This is the general form of Legendre's differential equation. Here, your variable coefficient is ax plus b. If order of derivative is n, then degree of this linear factor ax plus b is also n. In the second term, if order of derivative is n minus 1, then degree of linear factor ax plus b will be n minus 1. So this relation between order of the derivative and power of linear factor ax plus b will be the same. Then and then only we can say that given differential equation is in standard Legendre's differential equation form. And to solve Legendre's differential equation, we used to convert this variable coefficient form into constant coefficient form by using substitution. And here we substitute the variable coefficient, that is ax plus b is equal to e raised to z. That is, value of z is equal to log of ax plus b, just like the Cauchy's or Euler's differential equation. So since y is dependent variable, initially it is defined in terms of x. Now by using this substitution, we are converting variable x into variable z. Then by using chain rule, we can replace dy by dx as dy by dz into dz by dx. So since your z is equal to log of ax plus b, then from this relation we can find value for dz by dx, and this value will be 1 upon ax plus b into derivative of ax plus b with respect to x will be this. Now we substitute that value here. Therefore dy by dx is equal to dy by dz into a upon ax plus b. If we take this denominator term on left hand side, we get value of ax plus b into dy by dx can be replaced by simply dy by dz into a, where if we use new differentiation operator d such that d takes derivative with respect to new variable z, then we can replace this variable coefficient form of the derivative in terms of constant coefficient form of the derivative d in terms of z. So this substitution will help us to convert variable coefficient form into constant coefficient form. So similarly, we can generalize for second order derivative term as well. So similarly, we can consider second order derivative of y with respect to x. So it is nothing but derivative with respect to x of dy by dx, and since again we can apply the chain rule for this derivative with respect to x, so it is nothing but derivative with respect to x. So first we consider dy by dz into dz by dx. So we apply u into v rule for evaluating derivative of this product. So it is equal to, so by using derivative of product of two functions rule, we take derivative of first term, that is dy by dz, into second term as it is, plus first term as it is into derivative of second term, that is dz by dx. Now we substitute value for dz by dx. So it is equal to d by dx of dy by dz into this value is equal to a upon ax plus b. Same is the case with second term dy by dz into derivative with respect to x of a upon ax plus b. Now we apply chain rule for this derivative. We can rewrite it as derivative with respect to z into dz by dx. Now we can substitute, we have to take derivative of this function, so it will be kept as it is, dy by dz into a upon ax plus b, this term taken here as it is. So we are applying the chain rule for this derivative term only. Note this step, it is very important. You have to consider this dz by dx again, plus dy by dz into, so what will be derivative of this function? A is constant, a can be taken as it is, and derivative of 1 upon ax plus b will be minus 1 upon ax plus b bracket square into a. Fine. Again, value for dz by dx is a upon ax plus b, so we can rewrite it as a square upon ax plus b square into, so derivative of y with respect to z is taken 2 times, so it is nothing but second order derivative of y with respect to z minus a square upon ax plus b square into dy by dz. Now we can take the common terms inside. So this implies, since our left hand side is second order derivative of y with respect to x, we take a square upon ax plus b square outside. So this is nothing but d square minus d of variable y, since d represents derivative with respect to z. Now we take the denominator term on left hand side. So we can replace ax plus b bracket square into d2y by dx square, and it is replaced by a square into d minus 1 y. Now we can generalize. For the linear factor ax plus b, it is repeated 2 times, so we take coefficient of x, that is a, 2 times. Since derivative is of order 2, so we take 2 linear terms containing operator d, where d will take derivative with respect to new variable z. So since derivative is of order 2, we take two terms containing d, starting with d minus 0, d minus 1 and so on. So we apply the same logic for generalizing the things. If our factor is ax plus b raised to n into nth order derivative of y with respect to x, then since this factor is taken n times, so we start with a raised to n, where a is coefficient of x into, now we count the order of derivative, it is n, so we start with d minus 0, d minus 1, d minus 2 and so on, d minus n minus 1. These are the linear factors. These are n linear factors. So degree of this will be n, which is same as total order of differentiation. So from this we can rewrite equation number 1. Therefore equation 1 can be rewritten as an into, so this is the coefficient of an and it will be replaced by a raised to n into d, d minus 1, d minus 2 up to d minus n minus 1. Then second term in equation number 1 was a n minus 1 into ax plus b raised to n minus 1 into n minus 1, the derivative of y with respect to x, and it will be replaced by a raised to n minus 1 d into d minus 1, d minus 2 up to d minus n minus 2 into y and so on. a1 into dy plus a0y, and this whole left hand side will be equal to f of x, and since we have replaced x by some function of z, so right hand side will be obtained in terms of new variable z. So if we observe left hand side very carefully, for this differentiation operator d, coefficient will be a constant term every time. So we are getting a polynomial in terms of d, which is to be operated on dependent variable y, and on right hand side we get a function containing new variable z. So this is nothing but, this is a linear differential equation with constant coefficients. Now to simplify, the required general solution will be here complementary function plus particular integral, where complementary function is obtained from auxiliary equation. Since this d is a derivative with respect to z, this complementary function will be obtained in terms of z. Again, particular integral will be obtained from this f star of z. So again, value of particular integral will be obtained in terms of z. But this is not the required solution. So we have to resubstitute z is equal to log of ax plus b, that is ax plus b is equal to e raised to z in this general solution. So we get required general solution in terms of x, that is complementary function in terms of x plus particular integral in terms of x. So this will be the required general solution. So while solving any example on Legendre's differential equation, we have to take care of these three things. First thing is use the substitution. Variable coefficient ax plus b is replaced by e raised to z. Then use the replacement, convert variable coefficient form into constant coefficient form. Then solve that linear differential equation with constant coefficient by calculating its complementary function and particular integral in terms of variable z. Then reconvert that general solution in terms of x by substituting ax plus b is equal to e raised to z. And this is the most important part. because your final solution is obtained in terms of variable x. So this will be our required general solution. So let's take one example on Legendre's differential equation. So example we take is 2x plus 3 bracket square into second order derivative of y with respect to x minus 2 times 2x plus 3 into derivative of y with respect to x minus 12 times y is equal to 6x. So this is given differential equation. Now we consider whether it is in standard Legendre's differential equation form or not. So first, the variable coefficient is 2x plus 3. It has degree 2 when derivative is of order 2. In next term, 2x plus 3 has degree 1 when derivative is of order 1. So it is in standard Legendre's differential equation form. So we can consider the given differential equation 2x plus 3 square into second order derivative of y with respect to x minus 2 times 2x plus 3 into dy by dx minus 12y equal to 6x as equation number 1. Now, by using standard method of solving, we substitute the variable coefficient, that is 2x plus 3 is equal to e raised to z, that is value for z is equal to log of 2x plus 3. Since on the right hand side our f of x is 6 times x, so from this relation we can identify value for x only. So it is equal to e raised to z minus 3 upon 2, or we can consider f of x is equal to 6x. We substitute x is equal to e raised to z minus 3 by 2. So it is equal to 3 times e raised to z minus 9. So this will be your function in terms of z after the substitution. By using this substitution, we can replace the variable coefficient terms in the given differential equation. And in the given differential equation, there are two variable coefficient terms. So it can be replaced by, so we replace 2x plus 3 into dy by dx is equal to. So first we consider the linear factor or the variable coefficient 2x plus 3. Here value of a is equal to 2. It is appeared only once, so we start with 2 raised to 1 into. Since derivative is of order 1 only, so we take derivative differentiation operator d operated on dependent variable y, where d is derivative with respect to new variable z. And the second term, that is 2x plus 3 bracket square into second order derivative of y with respect to x. Again, value of a is 2, it is appeared 2 times into, since derivative is of order 2, so we take two linear factors d into d minus 1. So by using these two replacements, equation number 1 reduces to, therefore equation 1 becomes. So we substitute the first term 2x plus 3 bracket square into d2y by dx square will be replaced by 4 times d square minus 4 times d into y. Then second term is minus 2 times 2x plus 3 into dy by dx, and 2x plus 3 dy by dx will be replaced by 2 times d into y. The constant term is minus 12y is equal to 6x, and that 6x is replaced by this function 3 e raised to z minus 9. that is 3 e raised to z minus 9. So we can simplify. So it is equal to 4 times d square minus 4 times d minus 4 times d minus 12y is equal to 3 e raised to z minus 9. Please check my calculations. This implies 4 times d square minus 8 times d minus 12y is equal to 3 e raised to z minus 9. We can simplify by taking 4 common from the auxiliary equation. Therefore, auxiliary equation reduces to d square minus 2 times d minus 3 into y is equal to 3 by 4 into e raised to z minus 9 by 4. We can call this as equation number 2, and which is linear differential equation with constant coefficients. Agree with this? Now, the required general solution will be obtained from complementary function, which is to be calculated from the auxiliary equation, and particular integral, which is to be calculated from this function containing variable z. Therefore, to find complementary function, we consider the auxiliary equation, that is phi of d, which is nothing but d square minus 2d minus 3 is equal to 0. So if you find roots of this equation, so what will be the roots? So this implies roots of this equation will be 3 and minus 1, because product of these two will be minus 3 and 3 minus 1 will be 2. So the required complementary function will be c1 into e raised to 3z. Here we do not take variable x because this d is, since d is derivative with respect to independent variable z, so we take independent variable here in the exponential function, and c2 times e raised to minus z. So this will be the required complementary function in terms of variable z. For converting this complementary function in terms of x, we put e raised to z is equal to the substitution 2x plus 3. Therefore, your complementary function in terms of x is nothing but c1 into value for e raised to z will be 2x plus 3. Its power, if you take 3, so it will be cube. So value for e raised to 3z will be 2x plus 3 brackets cube plus c2 times e raised to z raised to minus 1. If this power is minus 1, so it will be e raised to minus z. So the right hand side will be 2x plus 3 raised to minus 1. So this is our required complementary function for the given Legendre's differential equation. So now we denote this by equation number 3. Now to find particular integral. To find particular integral, we operate the auxiliary equation on the function of z. That is, we operate the given differential equation, that is d square minus 2 times d minus 3 on f of z, where f of z was 3 by 4 into e raised to z minus 9 by 4. Here, for the constant term 9 by 4, we can consider it is e raised to 0z. Fine. So we apply shortcut method formulas for both exponential functions. Here value for a is equal to 1, here value for a is equal to 0. So out of these two values, we check whether there exists case of failure or not. So before solving this, we consider since auxiliary equation is d square minus 2 times d minus 3. If we replace d by 1, since our shortcut method formula for exponential function is replace d by a, so we replace d by 1. So this value will be 1 minus 2 minus 3. So it is equal to 1 minus 2 is minus 1. So this value is equal to minus 4. So since this is not equal to 0, there is no case of failure. Again, for the same auxiliary equation, if we replace d by 0, so this value is equal to minus 3, which is again non-zero. So we can apply shortcut method formula directly. So particular integral is equal to 3 upon 4 as it is. We replace d by 1 and that non-zero value is minus 4 into the same exponential function as it is. Minus 9 by 4 into 1 upon 5 of 0, which is minus 3 into e raised to 0z. So this implies the required particular integral is minus 3 times e raised to z upon 16 minus minus plus 9 upon 12. Is it correct? So this is the required particular integral in terms of z. Again, if we substitute, z is equal to log of 2x plus 3. So required particular integral in terms of x can be written as minus 3 by 16 and e raised to z is 2x plus 3 and plus 9 by 12. So this will be the required particular integral. We can denote this particular integral by using equation number 4. Therefore, from equation 3 and 4, the required general solution in terms of x will be c1 2x plus 3 brackets cube plus c2 2x plus 3 raised to minus 1. Now particular integral is minus 3 by 16 into 2x plus 3 plus 3 by 4. That is nothing but 9 by 12. So this will be the required general solution for given Legendre's differential equation. So this is a required general solution. So in this way we have solved Legendre's differential equation, and sequence to solve any Legendre's differential equation is: step 1, substitute the variable coefficient of the form ax plus b is equal to e raised to z. Then by using this substitution we can replace the variable coefficient form of the differential terms in the given equation by using formula ax plus b raised to n, where n can be anything, into derivative of y with respect to x n times. It will be replaced by a raised to n into d minus 1 up to d minus n minus 1 y. By using this replacement formula, convert given differential equation into linear differential equation with constant coefficient. Then that linear differential equation will be converted in the form of phi of d into y is equal to f of z, where d is derivative with respect to z. Then in step 3, find the complementary function and particular integral. So find complementary function in terms of z, replace z by log of ax plus b, and then find complementary function in terms of x. Similarly, find particular integral in terms of z, replace the z in terms of x, and find c. Then step 4 will be required. General solution is complementary function in terms of x plus particular integral in terms of x. So remember these 4 steps and follow the sequence to solve any Legendre's differential equation. So take one example for your exercise. If you have any doubts in the solution, we can discuss that problem in the next session. Suppose that example will be 7 times 2 plus x square into second order derivative of y with respect to x plus 8 times 2 plus x into dy by dx plus y equal to 4 times cos of log of 2 plus x. Now again, hint is it is already in standard Legendre's differential equation form. So your hint is substitute the variable coefficient 2 plus x is equal to e raised to z. Therefore your function will be converted to, therefore 4 times cos of log of 2 plus x will be equal to 4 times cos of, your value for z will be log of 2 plus x. So we use this value here, so it will be simply cos z. So this is your required function in terms of z. Now the main task is what will be the replacement for these variable coefficient so that you convert it into linear differential equation with constant coefficients. The right hand side will be this function in terms of z. Find complementary function and particular integral. All the best. Thank you.